This is the first time I'm here on this side of the audience. So it's like a milestone achievement for me in life. So very happy to be here. Oh, hi Manish. So I'm going to be talking about a coarse version of a very classical invariant, which is called the Lusternik-Schnirelmann Category. Now, before we start defining all these things, I would like to give some motivation. Okay, why? What brought this up? In general, what's the motivation behind coarse geometry from one perspective? Okay, now one of the first examples of very big problems was this so-called coarse Baumgarten. I don't know how to pronounce it, but Baumgarten's conjecture. She assumed that you have a proper metric space, one can construct the so-called row algebra from it. These are locally compact finite propagation operators on this tensor product. Point is, only the large-scale properties of X survives in it. We don't need to know the definitions yet. This is just the motivation. So the conjecture is, for a proper metric space of bounded geometry, there exists a coarse assembly map from the K homology of the space to the row algebra to the K theory of its row algebra. And the conjecture is that this is an isomorphism. Now, it's been open for many, many years. It's known for certain classes of spaces, but overall, it's open. Now, I personally am interested in group. So for a finitely generated discrete group, gamma, one can choose a set of generators and make that into a metric space using the word metric. Under this metric, the Coarse-Baum conjecture implies an even bigger conjecture, which is called the strong Novikov conjecture. Now, I am not going to give the definitions for everything, but just the motivation is that it's a long, very old conjecture, and a lot of progress have been made in it, to the point that we know that for all of our known classes of groups, all of the most known classes of groups, we know that Novikov conjecture is true. But all of the proofs are very distinct from each other. There's no uniform way of proving it. Now comes a notion of dimension. I'm going to define asymptotic dimension properly later on, but for now, it's just a notion of dimension. You can imagine it's as a large-scale analog of our usual notion of covering dimension or Hausdorff dimension. Essentially, you just take the look at a space and go to infinity, look at it from far enough, and see what it looks like. It's a quasi-isometry invariant. We'll have the definition later on, but essentially it's rigid. Now, in 98, Goulian Liu proved that if you have a finitely generated group gamma with finite asymptotic dimension, he could give an embedding of that group inside a Hilbert space, which in turn proves that if it's finitely, so if it has a finite classifying space, so if the group is geometrically finite, it can satisfy the Coarse-Baum it will satisfy the Coarse-Baum conjecture and hence Novikov conjecture. So for all asymptotically finite groups, since 98, we know that the Novikov conjecture is true. Now, many groups are known to be asymptotically finite. For example, hyperbolic, nilpotent groups, solvable groups, arithmetic groups, and mapping class groups of like good enough surfaces, not everything, but for compact surfaces, we know it's asymptotically finite. But for many other groups, it's not known. For example, outer automorphisms of SMs. And for heli groups are kind of groups which act on injective spaces, for example. It's not known. So our motivation is we would like to define another invariant, not just asymptotic dimension, which will essentially be smaller than asymptotic dimension. So even when asymptotic dimension is infinite, we can hope to get finite values of that invariant. So the final goal, like that's the long goal, is to find a new class of groups satisfying the Novikov conjecture. That's the large program. I will give two constructions. One of them was done in 92-ish. Another one is me and my advisors work recently. Conventions, all metric spaces are assumed to be proper, so no function spaces. Closed balls will be compact. Most of the theory in coarse geometry can be stated for general sets with coarse structures on it. I'm not going to do that. I'm not going to define coarse structures for the sake of time. We're going to only deal with metric spaces. And not only metric spaces, proper metric spaces. Also, every invariant on these slides is reduced. So usually there's two notions of LS category. One is reduced, one is unreduced. The reduced version makes the formulas look prettier, so I'm going to use reduced. So the rest of it we'll understand a little later. Okay. Now starts the bit of math. A brief introduction to the classical LS category. So this is by Lusternik and Schnirelmann paper in 1934. So by the way, sorry. Category here doesn't mean the category theoretic category, is just a numerical invariant. So this arrived before category theory was a thing. So they just called it category and the name stuck. So let's start with a basic definition. The LS category is the smallest n for which a space X can be separated into n+1 contractible subspaces. So in some ways, it's like the next best thing to contractibility. If you don't have a contractible space, you ask, okay, can I separate the space into subspaces which are contractible? Okay. So these inclusions, null homotypic means AI not necessarily contractible, but the inclusion of AI is null homotypic. So AI can be contracted inside X, not inside itself generally. The same point I just made, this is necessary to show homotopy invariance. Some examples, well, obviously from the definition, category is 0 if and only if the whole space can be contracted to a point. So it's the simplest possible example. Now, spheres. Spheres are not contractible, so category cannot be 0. But you can always separate a sphere into top and bottom half, each of which can be contractible. Therefore, category of a sphere is always 1. A similar argument you can show that suspensions are either 0 or 1, because suspensions are essentially you're joining spheres. This one requires a little bit more work. So for any sort of invariant, you want to know the class of example for which you can invariant. RPN is one such class of example. One can construct this n+1 coverings of n+1 open sets in RPN. If you imagine the sphere model of RPN, you can inductively take away hemispheres. So you first take away the n-1 disk, then you take an n-2 disk from one of the remaining parts, and you inductively peel away disks. to get n plus 1 covers, n plus 1 open sets. A similar argument somebody mentioned yesterday, it actually shows that CPN is also LS category n. Category of the n torus is also n. We will end up proving this shortly later. Okay. Now, in general, calculating LS category is really hard. Like, only these examples before were kind of toy examples. If you're just given a group or given a space, it's really, really hard to compute LS category. One can give covers, one can give open covers that can bound it from above, but usually lower bounds for LS categories are hard. One of the lower bounds which we have is coming from cohomology. So let's define the cup length as the least k such that there exists at all the k plus 1 cup products vanish in the reduced homology. So it's the largest k such that there exist k homology classes whose product is non-zero. Okay. It's kind of the order, multiplicative order of the cohomology ring. And the first theorem is for every commutative ring R and for every topological space X, the cup length gives you a lower bound. So the proof is very simple, but it's very interesting that this is true for any possible ring and any possible space X. There's no conditions on anything. One can even say that this is for any well-behaved cohomology theory, not just for singular simplicial cohomology or anything. Okay, just follows from the Steenrod axioms. For example, an application of this lower bound would be that the cohomology ring of the n tori is an exterior algebra on n generators. Each of those generators is of degree 1. Therefore, the cup length of the cohomology ring is n. That gives us the LS category for torus is at least n. But one can always construct an explicit open cover of the torus with n plus 1 open sets such that each of them are contractible. It's a nice exercise to show that it's also dominated by n. Okay. One can also use this theorem. So, for a path-connected, locally contractible, paracompact space X, so path-connectedness means path-connectedness. Locally contractible means around every point. You have a neighborhood which contracts to the point. Paracompactness is just big brother of compactness, where instead of saying every cover has a finite subcover, you say every cover has a locally finite subcover. So for every such space, category is bounded above by dimension. We're going to come back to this later on. By the way, this proves that for the n torus, the dimension is also n. So this proves that LS category is bounded above by n. Okay, nice. So that shows that. This is a typo. Do not. This is not true. So I mean, the statement is true, but the same argument doesn't give it. We're going to ignore the same argument part. But category of RPN is n. I think I meant to write RPN because RPN is also n-dimensional instead of CPN. CPN is 2 n-dimensional. But again, this as we saw before, the cup length theorem is true for any such n R, any such x. So naturally, it's a little too good to be an optimal lower bound. So there are spaces with cup length over rational 1, but the LS category is infinite. So it's not a very efficient lower bound. Easy to compute though. Now, why was Lusternik and Schnirelmann looking at this quantity is that they were looking for critical points of smooth functions on manifolds. Morse theory wasn't a thing yet. Eventually, it became a thing. So they were only considering any smooth function, so they didn't require their functions to be like all the critical points to be non-degenerate. So let M be a smooth manifold, and I think I missed another condition. Let M be a smooth compact manifold. There's some more condition. If M is a smooth compact manifold, then any smooth function has at least cat M plus 1 many critical points. So if you write crit of M as the minimum of all such number of critical points for any smooth function, you have the following inequality. There exists at least this many critical points for any smooth function. Okay. But later on, if you have Morse functions, Morse theory gives a little better balance for it. Okay. But Morse theory also requires your functions to have non-degenerate critical points, which we don't always have. Okay. This is the motivation for LS category. Now, what do we want? We want a numerical invariant like LS category defined by small sets of some sort. We want some bounds, both lower and upper, hopefully some algebraic bounds, some geometric bounds, and we want the invariant to be an invariant under some notion of homotopy. Okay. The rest of the talks is two such programs carried out in two different situations. One is in the proper homotopy category, and the second one is the coarse homotopy category. The first one is the proper LS category. This was done by 4 authors in 92. They wanted to study LS category in the scenario of non-compact spaces, but they were still in the continuous setting, so they had continuous maps. They just said everything needs to be proper as well, not just continuous. So you define the category whose objects are Hausdorff locally compact, sigma compact spaces, and whose morphisms are proper continuous maps. Proper being inverse images of a compact set is compact. Well, note that you're defining beta infinity to be all non-compact spaces, but one can embed any compact space inside beta infinity by just taking the wedge with R plus. One can also show that this construction, just take the wedge with the ray, is functorial. So all the nice properties hold. So the category of all compact and non-compact spaces sit inside beta infinity decently. Here comes another point which we will come back to later as well. If you have an unbounded space, you can't always expect it to be contractible to a point. Why? Because that breaks properties. Contracting an unbounded set, deforming an unbounded set to a point is not good in the large scale settings. We want a deformation that is compact, that is proper, right? So base points are not exactly what you want here. Because if you say we want a space to be contractible and you say to a point, then only compact sets can be contractible. Nothing else can be contractible. So you choose the next best thing. Instead of a base point, you choose a base ray. So at the boundary, those become base points. So this is, I don't know what year it was, in the 80s, I believe. This is a result which says that any space in this category of T2 locally compact, non-compact spaces every space admits a base point, basically. Or it admits a map to a base point. And it's unique up to proper homotopy. That's not trivial, but that's what enables us to construct a lot of things in the future. Basically, a closed set is properly deformable to the ray if there are a retraction and a ray, making the triangle formed with the inclusion commute up to proper homotopy. I don't know if I've included the diagram, but I'm going to just say it here. If you have a closed subspace X, what we want is the subspace to factor through the ray. If this diagram commutes, we say, if this diagram commutes up to homotopy, proper homotopy, we say this guy is properly deformable to R plus. So similarly, it's properly categorical if some closed neighborhood is properly deformable to R plus. An open cover is categorical if each of its member is. So now we're reaching the definition for an LS category. The proper LS category is the least n such that X admits a properly categorical open cover with n plus 1 elements. And of course, if there exist no such elements, then it's infinite. Also, this is one can think of this picture as an example of a properly categorical set. The shaded region is an unbounded set going off to infinity, but this homotopy only collapses finite boundary, finite diameter set too. So this homotopy is a proper homotopy. So these are the kind of spaces that we're looking at. You can think of it in the boundary, we're looking at LS category, but in the interior of a set, we're looking at the proper LS category. Yeah, but this is just intuition. Basic properties. Obviously, LS category is less than equal to proper category because if you have a proper covering, proper homomorphism, proper deformations, that those are continuous deformations by itself. So category is strictly less than or equal to X, strictly less than or equal to proper category. Again, proper category of a space is 0 if and only if it's properly homotopic to the ray. Again, it's a proper homotopy invariant. So if it's a proper retract, then p cat of A is less than equal to p cat X. So if there's a homotopy equivalence, you have p cat of X will be equal to p cat of Y. This is not that important for us. I just put that there. Interesting thing is it satisfies the subadditivity condition, just like most dimensions. So under product, it's at most the sum of its individual terms. Okay, it's not always equal. There are counterexamples and everything. Okay, now ends of a space give a lower bound to it. So define the fundamental ends of a space to be the inverse limit of a space, and look at the bigger and bigger compact spaces. Their complements, take the path components of the complements and take the inverse limits. You get the ends. Now, the cardinality of the ends is a lower bound for proper category. So essentially, if you have two ends, you need at least too many sets. You can't properly deform one end to the other. So if you have to deform, you need at least as many ends as you have sets. Yeah, it's just what I said. More interesting bound is an upper bound. So here as well, the Hausdorff covering dimension gives you an upper bound of the proper category. So if it's a locally finite cell complex with exactly one fundamental end, then we have an upper bound. Well, we need one-endedness. If we have more than one end, we just look at each end separately and you apply this inequality on each end. Basically, it's a similar inequality like cat x is less than equal to dimension. There's also a stronger version of pcat. I'm going to just ignore that for now. We're going to look at the lower bounds. There are several cohomology theories which are proper homotopy invariant. The usual cohomology theories are not proper homotopy invariant. But one can look at cohomology with compact support, so singular cohomology with compact supports, or you can look at the Czech cohomology, Alexander-Spanier cohomology with compact supports. All of these cohomologies are invariant under proper homotopies. Some other examples. The point is, under each of these cohomology theories, one can define cup product and cup length, therefore. So for each of these cup product, each of these cup lengths, give a lower bound for proper category. Examples for the Euclidean spaces, it's not properly contractible, but you can look at the left half and right half and contract each of them separately. So pcat of Rn is always 1. For compact, Hausdorff cat x equal to just proper cat of x cross R plus. So it agrees with the notion of LS category in the proper situation as well. This is an interesting example, also a nice exercise. If you look at the line and you keep attaching spheres, one can show that you need exactly 2 spaces to properly contract these 2 lines. If it's a non-compact surface with one end, then it's 1 if and only if it's R2, and otherwise it's 2. These are results from their paper, and I'm just going to go over the results, not prove anything. But yeah, that's nice. That's an example of where subadditivity is shown. So if you take the product with R plus, anything can be collapsed to R plus. Therefore, the category of the product may not be equal to the sum of the categories. It's strictly less, actually. Okay, that's just a flavor. But one problem with this construction is that they always require continuity. Now, I don't want continuity. I want something that is invariant under quasi-isometries, or even a broader notion of coarse maps. Now, I'll try to define what setting I'm talking about. So let's say metric space is proper if closed balls are compact. Our category will have objects as proper metric spaces, and morphisms will be closeness classes of coarse map. We'll define that in the next slide. Both of them need some unpacking. First, we're going to define what I'll call a coarse embedding. So essentially, any function is a coarse embedding if the distances in the image can be bounded by some function of the distances in the pre-image. There exists a lower bound and an upper bound. We'll call them rho 1 and rho 2. Note that this is like a very general form of a definition for a kind of a function. So quasi-isometries, bi-Lipschitz functions, etc., those all fall under these classes for different kinds of roles. In literature, a coarse map is slightly different concept. For the purposes of this talk, we will call these coarse embeddings as coarse maps. Okay. They're slightly different. I'm not going to go into the differences now. So, two functions, we'll call them close when they are uniformly distant from each other. The distance between them is uniformly bounded by some constant. So, closeness is an equivalence relation. If A is close to B, B is close to A, and then ABC transitivity, you can all see that. Therefore, it forms an equivalence class. So you just look at maps under this notion of equivalence. And then the usual definition, X and Y are coarsely equivalent if there exist coarse maps going from X to Y and Y to X such that their composition are identity in both directions. Okay. Now, some of the familiar maps that you might have encountered before is, one of them is quasi-isometric embeddings. So, quasi-isometric embeddings are just coarse maps where rho 1 and rho 2 are linear. And it's by Lipschitz when rho 1 and rho 2 are, quasi-isometrics are coarse maps when rho 1 and rho 2 are affine maps. And by Lipschitz if rho 1 and rho 2 are linear. So we have strict inclusions. One can come up with counterexamples, it's not that hard. So, examples of coarse maps. The floor function. Coarse maps need not be continuous. And one can have the inclusion from Z to R, also a coarse map. So, Z and R are coarsely equivalent. Same argument shows that the integer lattice is also coarsely equivalent to the plane. Slightly non-trivial example by Milner-Schwarz lemma. If a group acts properly and co-compactly by isometries on a proper geodesic space, then any orbit map is a quasi-isometry. So our hyperbolic group, etc., acting on hyperbolic space, they produce quasi-isometries and hence a coarse equivalence. So this is what we want. We want an invariant for groups which is rigid under choosing different generators, choosing different metrics. So this is what we want. A similar example, take t to square root of t. It's coarse, but not a quasi-isometry. This is another non-trivial example. If you have a complete simply connected manifold of non-positive sectional curvature, then we know that the exponential map from the tangent space to itself is diffeomorphism. It's a distance increasing diffeomorphism. So you can have its inverse, which will be coarse, which will be distance decreasing. So in certain cases, we can upgrade this to a homotopy equivalence, but we'll come to that later. And some maps that are not coarse. Bounded maps, obviously they're not proper. Projections also not proper because you're collapsing entire lines into points. X going to x squared because the distances get arbitrarily large. Exponential maps, the same reason why x to x squared is not coarse. But now we have a notion of coarse maps, we need a notion of homotopy between these coarse maps. This is kind of a more subtle idea because there have been attempts at generalizing notions of homotopy in different contexts, but it took a while to get to a right definition. The idea is that you can think of a classical homotopy as a deformation in the time variable. So for each value of t, you have a different embedding, not necessarily embedding, but different map, and you change those maps according to the time t. But the problem with that is, if you just say, I'm going to deform every point for the same time t, you're going to have a problem with properness. So what do I mean by that is that suppose we have a space X and X cross the interval here. Any coarse map from here to X, if we just have a coarse map from this cylinder is quasi-isometric to X itself, right? Because this is length 1. So you can just squeeze the cylinder into X itself. Therefore, the only possible coarse maps from the cylinder to X are the ones which make it identity. So we want a different notion of a cylinder. We can't just take the same uniform height over all. So we have to choose a base point, let's say x0, and let points far away from X move for longer time. That's the basic idea. So fixing a base point gives you a standard choice of a coarse map X to R plus. You just look at the distance from x0 to any point. So you define our new notion of a cylinder. You look at the graph of the coarse map P and look at the area under that graph, and you call that the cylinder. This is what it looks like. So instead of having the flat cylinder over here, you look at a point x0, and as the further you go from X, the more leverage you have into deforming. Okay. And you note that there exists an image of X on the bottom, which is just X cross 0. And also there exists an image of X on the top, like so. So there still exists two images of X in here, just like there exist two images of X here. So you do the usual homotopy theoretic constructions here. Define a coarse homotopy is a coarse map from this P cylinder for some coarse P. It's a homotopy from the top part and the bottom part. And we write F is coarsely homotopic to G. For each X, the slice is a coarse path in Y of length path of X. So for each X, you have these paths. Their images in Y give you different paths, and each path is of length Ex. So some basic properties: if F and G are closed, obviously they are homotopic. This is a non-trivial statement. Homotopy is an equivalence relation. This requires some work. For path metric spaces, the choice of our coarse function does not matter. This is highly non-trivial, and its proofs requires at least like 3 pages of complicated calculations. But essentially, you can just choose a P0, and for every choice of other P, you get the same thing. So you call a coarse map is a coarse homotopy equivalence if there is a inverse map such that both compositions are coarsely homotopy equivalent to identities. Now, this is a non-trivial example of a coarse homotopy. Let M be a complete simply connected and of non-positive sectional curvature manifold. I forgot to write manifold. Manifold. Then exponential map is a bijection, but its distance increasing, so it's not going to be coarse. But its inverse, you can say that it's coarse. The more non-trivial part is there exists a coarse homotopy inverse of log, which is not exponential. So there does not exist any coarse inverse of log, but there always exists a coarse homotopy inverse of log. And its construction is almost inductive, and it's kind of tricky, but it's also very sweet. So Euclidean plane and the hyperbolic plane, they are coarsely homotopy equivalent. They're not coarsely equivalent, but homotopy equivalent. There's not coarsely equivalent because one of them is hyperbolic, one of them is flat, so they can't be. There you go. We have a basic idea of the coarse category now. Now let's look at the coarse LS category. Now, once we have notions of coarse homotopy, you can similarly define coarse categorical sets. Coarsely categorical sets, I forgot to write the definition here, but they're just sets like this, which can be coarsely homotop to raise for us. Okay, so you just count the number of pieces you want to, so that each of those pieces are coarsely deformable to lines. So from the definition again, coarse category is 0 if it's coarsely homotopy equivalent to the ray. And if there are coarse maps, f going from x to y and g going from y to x, so we have x is dominated by y. So if we have a commutative diagram like this up to coarse homotopy, then coarse category of x is strictly less than or equal to coarse category of y. So corollary of that is just if they're coarsely homotopy equivalent, then coarse category agrees, because you can do the same thing with y and x. Oops, sorry. So since we have a coarse homotopy invariant now, we can use Milnor-Schwarz lemma to say that for a group gamma, you define the coarse category of the group gamma to be the coarse category of a space that gamma acts on nicely. Okay. In particular, coarse category does not depend on a choice of generating set. Any word metric will do. Did I say finitely generated? This should be finitely generated. Assume everything is finitely generated, finitely presented. Examples. There aren't many examples here just because it's so complicated. But obviously, coarse category is 0 if and only if x is coarsely homotopic to the ray. Coarse category is 1. Coarse category for the Euclidean space is 1 for every n greater than or equal to 0. And hence, coarse category is 1 for every complete simply connected M of non-positive sectional curvature, because of, again, Milnor-Schwarz lemma. And sorry, not Milnor-Schwarz lemma, it's because of this this construction. For the infinite binary tree T2, no two distinct geodesic rays are coarsely homotopic. So coarse category of T2 is infinity. So basically, this case. Here, no two distinct geodesic rays can be properly defined from one to the other. So each of those rays give a different element. But I don't think I mentioned this in the slide. But imagine a similar tree, but you embed it into a strip of finite width. Okay, so as you go up and up, the tree gets more and more squished. This has coarse category 0. Why? Because it's just the distance between them is at most 1 or at most d, so you can discontinuously deform everything into one line. So it's a metric property, not a topological property. Yeah, I wonder why I put this picture here, not before. This is just an example of why coarse category of the plane is 1. You can't deform the whole plane into a half ray because that would break continuity. Not continuity, that would break properness. But you can break the plane into 2 halves, and each half can be deformed into each of these rays. Now, we had the notion of proper category before, and now we have a notion of coarse category. So if our X is uniformly contractible and a nice enough space, we actually have an inequality that every coarse map here can be somehow made into a continuous map here. So you take a coarsely categorical covering here, you do some magic so to get continuous maps. So you can get a proper category, proper LS category. Intuitively, you start with the 0 skeleton and fill in the simplices. You can only do it because it's uniformly contractible, finite dimension. So for a geometrically finite group, one can show that the universal cover of its classifying space is uniformly contractible, and it also has nice properties. So for geometrically finite groups, our proper category is less than equal to coarse category. So we can stand on the shoulder of the giants there and use their lower bound for our lower bound, right? Because they prove that for any nice enough homology theory, the cup length of X is a lower bound for pcat. And now we have shown that it's less than equal to ccat. So this gives us a lower bound for ccat as well. In practice, most of the examples, at least for groups, this is an equality, not just an inequality. So it's not a bad lower bound. Now, how am I doing on time? Am I out of time? Or I think we have like 10 minutes. Okay. Okay. We need an upper bound. So what is an asymptotic dimension? Recall that a family of subset is uniformly bounded if each of those elements of the family are bounded by the same number, and are disjoint if the elements are all uniformly disjoint from each other by at least some number. You define asymptotic dimension to be less than equal to n if for every uniformly bounded open cover, there is a uniformly bounded open subcover. It should be subcover U of X, which multiplicity less than equal to n plus 1, which V refines. Okay, so I did mention it. Not subcover, but something that V refines. I'll give a picture. This is not the most intuitive definition, but the one that we use usually is that if asymptotic dimension is less than equal to n, if and only if for every scale R, there are R disjoint families of uniformly bounded subsets whose union is X. So you can think of U0 to UN as colors. So asymptotic dimension is n if there exist n plus 1 colors, each of which are, so there are n plus 1 colors and they are in patches. And each of these patches are uniformly bounded, and no two of these patches get arbitrarily close to each other, essentially. One example, asymptotic dimension of the plane is less than equal to 2. So I've tried to make them different colors. So if you look closely, there are 3 colors here. Let's say the purple ones are all uniformly distant, at least this much distant from each other. And you can see that for any n, any scale r, you can just zoom out this picture. So this tiling of the plane works for any scale. One can show that asymptotic dimension of the plane is at least 2 as well by some cohomological methods, but this is a nice way to visualize asymptotic dimension. Okay. Asymptotic dimension is a coarse invariant. So whenever x and y are coarsely equivalent, the asymptotic dimension are the same. Asymptotic dimension of then for every n, since Rn has asymptotic dimension n, Zn and all those things have also asymptotic dimension n. Asymptotic dimension of trees are 0 or 1 if it's a bounded tree or non-bounded tree. Now, the coarse version of the covering dimension is basically what asymptotic dimension is. So what we want to say, its coarse category is less than equal to asymptotic dimension. We almost have that. So let X be a coarsely bicommable proper geodesic metric space, which is also coarsely path connected. I haven't defined most of these things. Under some hypothesis, we can prove that coarse category is less than equal to asymptotic dimension. It's not always true, but proper geodesic metric space, that part is kind of important. We don't want to lose properness. Coarsely path connected just means that any two alpha and beta, any two coarse rays are coarsely homotopic. It's just the counterpart of path connected. Instead of points, we just have rays. So you take any two rays, you can collapse them into each other. So that's also required because if you have two different ends of the space, then asymptotic dimension just takes the maximum, but coarse category has to take the sum of them. So that part is important. The only part that is an artifact of the proof is this bicommable part. I'm going to say something more about bicommability. I'm not giving the definition just because it's a bit unintuitive, but examples of the bicommable spaces include hyperbolic spaces, flat spaces like cat0 complexes, like cat0 cubical complexes, and coarse path connectedness is also sometimes called coarse semistability at infinity. It's a coarse analog of the group theoretic notion of semistability as infinity. Now, bicommability is essentially what provides us with a way of collapsing balls at like large distances. So I'm gonna come back to bicommability in a bit, but for now, let's assume that bicommable spaces are nice enough. And for groups, they are kind of the only kinds of spaces you see. So what do we get for group? For a finitely generated bicommable group, which is coarsely path connected, we have this inequality. Because the proper metric spaces and all those things are taken care of by finitely generated groups. Corollary, if you don't want coarsely path connectedness, you can consider groups which are one-ended and semistable at infinity. One can show that they are the same families. This inequality holds there as well. So the only non-trivial part is the bicommability. The corollary follows because discrete group with word metric, one-ended semistable at infinity is if and only if statement with coarsely path connect. Yes, how restrictive is bicommability? There's a notion of bicommability in geometric group theory. You can think of it as existence of solutions of a particular kind of word problem. But examples are word hyperbolic groups, geodesics with common endpoints, fellow travel, cat zero groups. They are good. Biautomatic groups, so braid groups, Coxeter groups, finite type Artin groups, all of them fall into this category. More generally, any group acting geometrically on a space with a conical geodesic bicombing is good. I haven't defined it either. The problem is I don't know of any finitely presented group that is not bicombing. I have been trying for now 5 months to find some counterexample which is not bicombable. All the ones that I know are not finitely presentable. But if I can construct one, I can construct infinitely many. So given a bicombable group, one can construct more of them. Given non-bicombable group, one can construct more of them, but I haven't found any in the literature yet. So if somebody here is good at combinatorial group theory, I would love to talk. Where that leaves us. For geometrically finite gamma, we now have a nice chain of inequalities under the hypothesis of these two theorems. So we need one-endedness. Novikov conjecture can be reduced to groups with only one end nowadays. So one-endedness is not that big of a problem. The problem is bicombability. For groups where asymptotic dimension is not known to be finite, for example, outer automorphism groups, Heli groups, etc., or like some, I think now it's known for hierarchically hyperbolic groups as well. So yeah, these examples showing that a coarse category is finite might be easier in theory. It's just a smaller invariant. Open in the other direction too, is bicombability really needed? I don't know, because I just don't have any example. These are the references if somebody is interested later on, but thank you for your patience. Here's the QR code for the archive paper, and